Hello guys, welcome back. Márcio Marinho here, and we are going to talk about the BigO notation. Okay, the BigO notation for analysis of algorithms. Um, this module is broken down in three parts. So this is the first part, the basics. Let's go. The BigO notation is a mathematical notation to classify algorithms according to their running time and or space usage. What that means is we want to measure how fast or slow an algorithm runs and how much space it uses. So the BigO notation gives us this measurement. A good question is why did people came up with the BigO notation? They could have used many other techniques or workarounds. So there are many questions that need to get a good answer. For example, how should I know if my algorithm is efficient? Should I simply code and see what happens next? What about if I run in different machines? Is it ever gonna finish? Am I using too much memory? And on and on and on. So another interesting thing is how should we compare low-level or lower-level languages with some more high-level ones, such as C versus Java, Ruby versus assembly, and so on. Before answering all of that, so let's go back a little bit and talk about the growth magnitude, which is pretty simple. It comprises the input size growth. What I mean about that is if you are going to process 1 element, 10 elements, 100 elements, or 1 billion elements. So the question is how to measure that running time. So is my algorithm run faster if I run 1, 10, 100, or so on? If you go to this Wikipedia page, it describes the IPS, which is instructions per second. So that these are how many instructions a processor can run per second, which has this, well, a bit complicated calculation or equation. So the IPS is equals to sockets times core divided by socket times clock times IPS over cycle. It's a very, very, very difficult calculation to make. And if we go to measure our algorithms using this calculation, that's going to be really tricky. So what if we get a fast processor? So I went to that Wikipedia page and I got the fastest processor that came up at my site. So which was this one, the AMD Ryzen. I think that's the proper way to say that. So, and this processor can run 304 million instructions per second. So it's not, we're not counting one instruction, but millions of instructions per second. So that's it. So this is how powerful the processor is. If we want to do this calculation, that's going to be really difficult and cumbersome. And to make things worse, if you notice here, for each processor or each processor type, brand, and architecture, they all have different MIPS. So it would be really difficult to measure our running time for every single processor. So we would have different results for each of them. And we are not going down this path. So we have a better path to go. Then coming back to the BigO notation, so we have a kind of computation model, so which says that algorithms can be analyzed, measured, and studied, abstracting languages and machines. So we don't have to be worried about if we are running our algorithm in, let's say, laptop, or if you're running on a data center or anywhere else. So we can measure the algorithm, and we're going to have a kind of more or less precise measurement of it. How do we measure it? We measure counting steps. So how to count steps? Pretty simple. Every single operation is counted as one single step. It can be a multiplication, subtraction, addition, an assignment, an equality symbol, an if branch, or a function call. So these are counted as a single step. I would like to note and stress that subroutines and loops are not single steps. So I have commented here my code. So these are all single steps. I'm assigning variables, I'm summing, I'm printing, all single steps. But whenever we talk about loops, for example, they are not single steps. So they are multiple steps. So they are not counted as single steps. So what is the BigO notation about? The BigO notation is about the worst, average, and best case time complexities for any given algorithm, which are kind of numerical function targeting the size of the problem. That is a formal way of what I have said before. So we will be always looking at the input size. So as the input size grows, we want to measure what's going to happen. So another interesting thing about the BigO notation is that it's not intended to give a precise measure. So we're not going to see, oh, that runs in 35 milliseconds dot some nanoseconds. That's not what it's about. It's a more generic notation and measurement. So we don't have to be worried about precision because it works with a very nice approximation, which is good enough and does the job. Okay, more formally speaking, or a more mathematical way of speaking, so the BigO notation is used to classify algorithms according to how their running time or space requirements grow as the input size grows. That's the formal definition, which I took from the Wikipedia. If you want to go there and read, yeah, just do it. It has a lot more information that I have here in this slide, as I don't want to flood you with too much math, but it works seeing those running things as mathematical functions. That's it. Such as this example here, f of x equals to O gx as x tends to infinity. So just take a look for yourself. Function is a kind of metaphorical or abstract machine or black box that will take an input and will return an output, which takes something and returns something else. So again, there is another Wikipedia link here. You can take a look. But just bringing it back to our word, our Java word. So a function is a method. That's it. That's what a function is in our word, in our case. So I want to sum all the elements of an array. I'm just inputting that array, which is my input, which has the size, and I'm going through every element, summing them, and I'm returning the result, which is the sum of the array's elements. So best, average, and worst case scenarios. So this graph shows more or less how things work. So if we want to see that measurement as a graphical information, so that's the worst case scenario. That's the worst thing that can happen. That's the average case. That's the best case that can happen to our algorithm. What really matters is the worst case scenario. Why? Again, because that's the worst thing that can happen. And as an illustration, let's imagine I spent $5 buying a lottery ticket. So yeah, these are my numbers. And the worst case scenario is I do not win. Therefore, I lose my $5. So nothing else can happen. So that's the worst thing that can happen. So which is I bet $5 and I did not lose. Sorry, I did not win. So I lose my $5 on that bet. So best case, that's something we are not worried about, because the best case, it usually comes with a set of boundaries that we have no control over. So it's really meaningless to aim for the best case. For example, on that example I gave for the lottery ticket, if I win, for example, I get rich, I buy a mansion, a boat, and something else. So, but we all agree that the best case on betting on the lottery is extremely rare to happen. So, and there are a lot of conditions to that to happen. So I need to choose the right numbers, and they might be 7 numbers, and that combination is really hard to make it right. The average case is the same thing, so it's really unrealistic and non-deterministic, because it can be subject to people's appreciations or to people's imagination. So, for example, what is the average case for the lottery ticket? So, I don't know, I just wrote here. It could be, for example, I get my $5 back on every 30 tries. Yeah, maybe, maybe not. Again, and the same concept applies to algorithms. So we are always aiming to measure the worst case scenario. And that's it, folks. We just finished our introduction to the BigO notation, which was part 1. And see you next time on part 2, growth rates.